Page 2, I envision looking a lot like this when it's the actual test. Um, One thing I may add to this is instead of just showing you A, B, C, D, E, and F, I might add G on here, which would be where the rocket is touching the ground and coming to rest down there. So it's in the act of coming to rest. It's just touched the ground and it's coming to a stop. So on the real test, I may pick any of these A, B, C, D, E, or F or G, and then have you sketch position, velocity, and time graphs. So I'm going to explain what's going on here, and then I might talk about some other ones. The first, stage A. To do this right, you need to be familiar with what's going on, and you also need to be able to do graphing. So in this first stage, we've got thrust. So the rocket is accelerating upward. It's going faster and faster upward. So I'm just going to write A is positive and velocity is positive. So for the acceleration, you can just do a straight line across. It says you may assume that accelerations are constant. So you can, whatever the acceleration is, if it's in the positive or negative zone, just go straight across. And this positive acceleration can tell me the velocity because the slope of the velocity graph is the acceleration. So positive acceleration means I need to have positive slopes the whole time. And not only do I have to have positive slopes, but I need to have positive velocity. So this would be a positive slope for velocity, but the velocity is in the negative range, so that wouldn't be okay. So you just need an upward line like this, somewhere up in the positive velocity range. And the rocket's above the ground, so position-wise, we're in the positive area up here. And the same relationship between position and velocity exists as between velocity and acceleration. So the slope of this gives you these numbers. The slope of this gives us these numbers. So instead of explaining how to do this, I'll just look at it and sort of check my work by looking at the slope. The slope is 0 or close to it. The slope is positive, more positive, more positive, more positive, more positive. I didn't actually start my velocity from 0 here. So I'm going to fix it by making it like that. Alternatively, if I had made that 0 in the beginning, then I probably should have done velocity like this. I'm not going to be picky about this. What I do want to see is generally if the velocity is going up like this and the velocity is positive, then the slopes here should generally be positive and getting bigger. So positive slope getting bigger. And it's, you know, I'm not going to split hairs over whether, oh, it looked like that was 0 in the beginning, it should have been here. This and this would have been okay. But what you do need is an upward curve because the slope should be increasing. Okay, number 19. Number 19 is asking about stage F. And it says it's falling at terminal velocity. And terminal velocity, you need to know that that means acceleration 0. And if it's falling, then you should know the velocity is negative. So acceleration 0. And if the acceleration is 0, then velocity is not changing. So the slope of this gives me acceleration, and this should be in the negative region. And these numbers give me the slopes here. So negative velocity, negative velocity, negative velocity. I need to have negative slopes the whole way. And I have a negative slope the whole way. And since the rocket is above ground, there shouldn't be anything down here in the negative position range. So none of these graphs, we won't be using that or that or that because rockets are always in the air. Number 20, the rocket's on its way to apogee after thrust is ended. So when there's no thrust, there is drag pushing it back, and there's weight pushing it back. So the net force on this is going to be downward, and that means the acceleration is negative. The rocket's going up though, so the velocity should be positive. So I'm going to start with acceleration and just make it negative. We can assume, to keep things simple, accelerations are constant. So fairly constant acceleration over this little time period. In reality, it's more complicated than that, but I'm just going to make it negative. So if the accelerations are negative and the same, then the slope of the velocity graph should be negative and the same. And the velocity should be positive, so it shouldn't be down here in the negative region, it should be up there. Then to do this, I look at these numbers, positive, 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 but getting smaller. Positive and getting smaller. So I need slopes up here that are positive and getting smaller. This is the steepest positive slope, less steep, less steep, less steep. And really, if this flattens out, then this should be getting to 0. But I'm not going to be too picky about that. I'm just going to look at this, and I want to see a downward curve here and a decreasing line here. Whereas on this first one, I wanted to see an upward curve. So the questions were about A and B and F. If you had to do C, then the acceleration up at the top is negative 9.8. If it's at apogee, the acceleration is just negative 9.8, which is basically just negative acceleration. The velocity at the top is 0, and the graph would look like this. So here's my position graph. This is going to be, so this is y position, this is velocity, this is acceleration. So at the top, let me do it in pen, the acceleration is negative 9.8. You don't need a number, but it's negative 9.8. The fact that this is always negative means the slope of the velocity graph should be negative. And it should cross through 0 here, so there. That's when the velocity is 0. So if I show a graph of velocity for a moment, like when it's at the top, what you're going to see is right as it's almost at the top, the velocity is positive. Then at the top, the velocity is 0. And then as it starts to come down, the velocity is negative. And then the y position here, I've got a positive velocity, then 0 velocity, then negative. So the slope of this should be positive, then 0, then negative. Like that. So positive slope here, 0 slope there, negative slope. So this is what C would look like. If we did D, the rocket is coming down, and it doesn't give you a description here, but it'll say it's falling and it has not reached terminal velocity yet. So what that means is the weight of the rocket pulling it down is stronger than the drag pulling it up. So the net force is downward and the acceleration is negative. And also it's going down, so the velocity is negative. So in terms of these graphs, here's my y position graph. This is going to be my velocity graph. This is the acceleration graph. So I'll just make the acceleration negative. And since the acceleration is, like, these numbers are negative the whole time, then velocity needs to have a negative slope. And the velocity is negative, so I need to keep it down in this negative region. like this. I shouldn't be up here in the positive region because it's got a negative velocity the whole time and the velocity is getting more negative. And these are negative numbers and getting bigger, which means the slope of the position graph needs to be negative and getting more negative. And that would look like that, which is what it would look like as the rocket's falling down out of the sky. So this is the answer if you were supposed to do D. And E, if I give you that on the test, E is going to be a time when the parachute is just opening up and the rocket is slowing down. So it's basically the drag is really strong and the weight is less strong, and that would give us a net force that's upward. So if it's falling down and getting slower, then the acceleration is positive. The acceleration is upward and it's going downward, so the velocity is negative. So what would that look like in terms of the three graphs? Y position, velocity, acceleration. So acceleration is positive and constant. And positive and constant means the velocity slope needs to be positive and constant, but it needs to be, let me put a 0 in here, 0, 0, 0, positive, negative. It needs to be down in the negative region, like this. So velocity is negative, still negative, but slower. And then position needs to have slopes that do this. So this negative velocity tells us the slope in the beginning for position. Smaller negative velocity, smaller negative velocity, smaller negative velocity. So I need to have a slope that's negative but getting less and less negative. So that would look like this. Here the slope is intensely negative. Here it's a little less negative, here it's a little less negative. And the velocity is very negative, a little less negative, a little less negative. And the slope of this is positive the whole time, and the acceleration is positive the whole time. So that is what E would look like if you had that on the test. And then finally, if on the test I gave you G to do, that's when the rocket's falling down and it hits the ground and comes to a stop. So when it does that, it's got this really big normal force that's stronger than its weight, and that brings it to a stop because the net force is going to be positive. So it's still moving down. Its center of mass, if you drew a dot at its center, that would be getting lower and lower. That would be tumbling down as it falls. So its velocity is still negative, but the net force is upward. So this would be negative velocity, positive acceleration. Feel like we've already done that one. That's basically the same as E. So if I go back to it, where is it? Yeah, negative velocity, positive acceleration. So these are what the graphs would look like during the impact with the ground. So positive acceleration, we can assume that it's constant to keep this easy. These are all positive numbers, so velocity would have all these positive slopes. Need to keep velocity below the x-axis in the negative range because the rocket's still going down. And then we're going from big and negative to smaller and negative to smaller and negative. So the y position is going to have a big negative slope, smaller, 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 and smaller negative slope. And the y position should be above the x-axis because the rocket's always above the ground. So that explains the